the way that we use high-performance computing, particularly at the NERSC Center at Berkeley Lab, to analyze the echo of the Big Bang. So first of all, just to give you an introduction to what we're doing. So the universe starts in a Big Bang. We don't really know what that means. We just have a convenient term for it. As in many things in cosmology, we make up a good name for it and sweep the rest under the rug. Starts out incredibly hot, incredibly dense, lots of infinities floating around, and expanding. And the good thing about the expansion is that it then cools the universe down to a realm where we start to understand the physics. And as the universe expands, it continues cooling, and eventually, about 400,000 years after the Big Bang, it cools through the ionization temperature of hydrogen. Now, before that point, basically lots of free electrons, protons, photons, some neutrons. But as you go through the ionization, protons and the electrons combine, and you form neutral hydrogen atoms, and suddenly there's nothing for the photons to bounce off. So prior to that time, they were pinging around, bouncing off the free electrons, and then all the free electrons get sucked up, and it's like the fog lifts. And in fact, it's not a bad analogy to think of it as the surface of a fog. Inside the fog, the light's bouncing off the water droplets, get to the edge of the fog, and the photons just free stream. So as we look out into space, we look back in time, we look out to this point, about 14 billion minus 400,000 years back in time, and we see the edge of this fog. Wherever you are in the universe, you look out in space, you will see this fog. You'll see this edge. You'll see those photons that when they scattered in our direction, when they last scattered. So this particular photon was bouncing around in the plasma, and then at the epoch of last scattering, suddenly there are no more photons to bounce off, and it happened to free stream all the way to us, an observer here today. This photon bounced around, but it went off somewhere else. But wherever you are sitting in the universe, you can look out in space. There's no preferred position. We haven't violated Copernicus or Copernican principles or anything. We're just sitting wherever we are, looking out in space until we've looked back to this last scattering surface, 13 point some billion years back. So this is cosmic. These are the photons, primordial photons from the Big Bang, filling all of space. Wherever you are, you'd see them. It's microwave, because although at last scattering, the characteristic temperature of the universe was about 3,000 Kelvin, the ionization temperature of hydrogen, the expansion of the universe since that time has stretched the wavelength of these photons so that instead of being 3,000 Kelvin photons, they're now 3 Kelvin photons. These are very, very cold photons. And this is primordial, this is background, because these are the original photons in the universe. They're not photons that have been generated by fusion in stars, no other astrophysical process involved. These were the photons created in the Big Bang, coming all the way to us now. And so another analogy I sometimes use is that unlike the rest of astronomy and astrophysics, where they're looking at things generating light now, supernovae, stars, the stars in galaxies, whatever, we're looking at these primordial photons. We're looking at the wallpaper. They're looking at the furniture. Yes?
Do we know their original just by their energy level?
So maybe you could repeat the question.
Do we know they're original by their energy level? No, we know they're original because there aren't any other processes to generate photons going on at that point. So this is before anything has collapsed under gravity to form stars and have fusion going on. So we're on the building up stage from everything's primordial at this point. So the particularly interesting thing about these photons is they give us the earliest possible image of the universe. So if you think about, periodically there'll be an announcement that astronomers have seen the most distant supernova yet, the most distant quasar. It's at redshift 4, it's at redshift 5, it may be even at redshift 6. We're looking at redshift 1100. So this is a long, long way back compared to the objects that collapse under gravity and start making photons from fusion. So This gives us a very important lever arm. This is a unique snapshot of the universe at a particular epoch, well before any of the other sort of complicated astrophysics happened. The very existence of this, this microwave background discriminated between the two competing theories of the cosmos at the time when it was first observed, which were the Big Bang and the steady state. The steady state theory posited that the universe is as it is, always has been, always will be, and not very popular with the church. The Vatican actually came out in the 50s and said, no, the Big Bang is correct, let there be light. Fred Hoyle, one of the big proponents of the steady state theory, actually coined the term Big Bang as a term of abuse to criticize the theory. And of course, it got adopted and championed. But simply finding these photons, which was done completely accidentally, there's a group at Bell Labs using a Bell Labs radio telescope, and they were trying to zero it. It's this huge radio horn. So they pointed it at the part in the sky where they knew there were no radio signals, and they couldn't get it to zero. They couldn't get the temperature down, or the signal down. And they tried all kinds of things. And if you read the original paper, they talk about removing a white dielectric substance. That was the pigeon shit from the pigeons that were roosting inside the telescope horn. They took the pigeons out. They took them miles away. They let them go. They're pigeons, so they flew back and went back into the horn. They took them out and did something a little more terminal to them. Couldn't get the signal to zero. Meanwhile, down the road in Princeton, there was a group that was actually trying to design and build the very experiment that these guys were doing, Penzias and Wilson were doing. And when they heard, famously, the leader of that team got off the phone and said, we've been scooped. They went and told Penzias and Wilson what they were seeing, the echo of the Big Bang, and Penzias and Wilson got the Nobel Prize. So this set up a fine tension between the experimentalists and the theorists that goes on today still. Prize for the microwave background. So these photons are very, very cold. They're, as I say, 3 Kelvin. But what we're really interested in is the fluctuations in this background radiation. So the universe is extraordinarily smooth and uniform at this time, 400,000 years after the Big Bang, but it can't be perfectly uniform, otherwise nothing would ever happen. So there have to be tiny fluctuations, tiny overdensities and underdensities that will eventually collapse under gravity into the large structures we see today. So you need a tiny seed perturbation, and if it's slightly more massive, then it'll have a stronger gravitational field, it'll pull more in, and it's a one-way process. So the overmassive regions accumulate more mass, the undermassive regions become more sparse. These are the seeds of structure formation in the universe, so there have to be some perturbations there. And so in retaliation for Penzias and Wilson getting the Nobel Prize, the theorists would predict every generation, they'd say, we just need one more magnitude of sensitivity in the detectors and we'll see these fluctuations. And so the experimentalists would go off and work incredibly hard and come up with these amazing detectors and field the experiment and observe and see nothing. And so the theorists was, well, actually, we forgot about this other term. And so one more magnitude, one more order of magnitude, and you'll get there. So we went through this for about 5 orders of magnitude until finally, with the Kobe satellite, George Smoot and co., the fluctuations were detected. They were detected on a statistical level. You couldn't really see them in the map. It was dominated by noise, but you could, if you did statistical analysis of the data, you could see the tiny fluctuations in this primordial background, which are the traces of the seeds of structure formation. So that got the second Nobel Prize for microwave background research. So what do these tiny fluctuations tell us? Well, we have, up till this point, very largely been concerned with the fluctuations in the CMB temperature. That's what got. In the last few years and going into the future, we're much more interested in the polarization, an even fainter signal. But if we take those two measures of what's going on in the microwave background, that will tell us a lot of things. It will tell us all about cosmology. It will tell us about the geometry of the universe. It tells us that the universe is flat. It will tell us about the topology of the universe. You can start trying to look for matching patches of sky that would represent identifications in non-trivial topologies of the universe. It tells us about the composition of the universe, which I'll talk a little more about, but it's nothing like we expected. It'll tell us about the history of the universe, how old it is, how long it's going for, what the reionization history is, and so on. But the other thing we can do, which is very interesting, a wonderful property of the microwave background, is that we can use the universe, the Big Bang, as the ultimate particle accelerator. So, LHC is all very nice, but if you really want to get to high energies, if you want to get to the kinds of energies that we're interested in looking at grand unified theories, you'd need a ring as large as an accelerator ring with conventional accelerator technology. You'd need a ring as large as the solar system. In the current funding climate, that's going to be a little tricky. So we use the Big Bang. There is nothing more energetic. Now, the only downside of the Big Bang is, A, it's not a repeatable experiment, and B, there's been 13.7 billion years intervening. So you've got your event happens, and all this wonderful particle physics goes on at extreme energies, and now 13.7 billion years later, you get to observe the results of that. So there's a lot of interpretation that goes into, well, what happened way back then and what would it lead to now? But if we do that interpretation, then we can start understanding things like physics beyond the standard model. We know that the standard model of physics, the quantum field theory, is incomplete. We know that general relativity is incomplete. We know that they're incompatible with each other. The Big Bang and the universe as a whole is the fundamental testing ground for trying to unify these theories, or see where the extensions, what the missing pieces are and how we might extend them. And I'll talk about dark sector and inflation as we go. So I'm currently working on a satellite mission, the Planck experiment, launched in 2009. I've been taking data ever since. Very busy analyzing that data. The first results will come out next January. And that will give us the definitive measure of the temperature fluctuations in the microwave background. This is the most exquisitely sensitive detectors ever flown in space. It's going to cover the whole sky and will provide, as I say, this definitive measure of the temperature. Beyond the temperature, as I say, there's the polarization we're interested in, and there are two components of the polarization, much like in electromagnetism, we can decompose into E and B. We can decompose the polarization into an E and B field. And in particular, the B mode component of the microwave background on large scales gives us a very nice detection. It gives us the only detection of a signal generated by gravity waves coming from the inflationary epoch. So the inflationary epoch is a moment 10 to the minus 35 or so seconds after the Big Bang, where the universe, for some brief period, exponentially expands exponentially fast. No one really knows why. There are infinitely many theories of inflation. But it's necessary to give the universe we observe today, and it is predicted by, as I say, by many, many, many theories. We're trying to tie those theories to observations at the moment. They're a little zombie-like, very hard to kill. But a detection of the B mode in the microwave background would give us at least the energy scale of inflation from these primordial gravity waves. And when that is detected, that will be the third Nobel Prize in CMB physics. So we have a field that we've got two, and we've got a third one coming, probably sometime around 2040. But this has been an extraordinarily rich field, primarily because of this point, that this is the one snapshot of the universe that we get before structure starts forming. So when I started in this field, moved out to Berkeley in 97, and joined the Boomerang and Maxima teams, and was working at Berkeley Lab, and also working at Berkeley Lab were people like Saul Perlmutter, looking at supernovae. And as with many things in cosmology, one of the issues with trying to uncover what's going on in the universe is that you have degeneracies in any single observation. So you can make an observation and you can interpret it in some parameter space, but the parameters are degenerate. So typically you want to combine multiple observations to break the degeneracies, and also because it gives you a much better handle on your systematics. If you get two observations that say the same thing, that's better than one. If you get three, that's great. from completely different methods. So the Supernova Cosmology project was looking at supernovae as standard candles, so that you have a known absolute brightness, and then you see how bright they appear to you, and that tells you something about how far away they are. We were looking at the microwave background, this constant surface. So the supernovae tell you about the dynamics of space-time, and the microwave background was telling us about the geometry of space-time. And we measure those two things in these parameters omega, which measure the fraction of the critical density in various parameters. Now, the critical density is the density of the universe that gives you a flat universe, as opposed to, so a Euclidean space, as opposed to non-Euclidean spaces. So lambda is the cosmological constant. This was a term that Einstein introduced into the equations of general relativity in order to make the universe static, because at that point, everyone knew the universe was static. Even Einstein couldn't get over that everyone knows kind of thing. And then 5 years later, Hubble discovers the recession of the galaxies, and Einstein's, oh, I could have predicted that. And he called it his greatest blunder. Turns out it's 70% of the universe. But, you know, it's, as blunders go, it's a big one. So the cosmic dynamics is driven by the difference between the cosmological constant and the matter, and the geometry is driven by their sum. So on this omega matter, omega lambda plot, the supernovae results gave you this degenerate region, and the microwave background results gave us this region, also degenerate, but in a perpendicular direction. So when you combine them, you can isolate this region. Now, fortunately for the supernova folks, this line down the middle here, the flat universe, was what everyone knew the universe had to be. So when they came out with their results slightly before the microwave background results, they just assumed flatness and said, okay, this is what the universe looks like, this point here. Then a year or so later, we came out with the results that confirmed the flatness, and yes, indeed. We sit at this point, somewhere in this point, and now there are many other observations of that. There's another observation of clustering that gives a degeneracy around here, but everything converges on this kind of value that tells us that the universe is 70% dark energy. No idea what that is, so we give it a nice name and sweep it under the rug. What we do know about it is it's got negative pressure. So this is the energy of the vacuum that is causing the universe to expand. And it's causing the expansion of the universe to accelerate, even. No one was expecting that. 25% dark matter. Don't know what that is. But it has to be there because if you look at the way that galaxies rotate, you can see that there has to be a lot more mass than just the visible mass. 5% stuff we know about. So we've quantified our ignorance at the 95% level. We have a lot of job security. But it does pose these rather embarrassing questions. What is this 95% of the universe that we're missing, that we can sort of infer the presence of? What's it made of? Surely it has to tell us something about the shortcomings in our current theories, particularly of fundamental physics at the highest energies. So these are the questions we're left with. What, and more particularly why, is the dark universe? So we want to observe the microwave background. So we want to observe 3 Kelvin photons, and we want to detect milli and micro and nano Kelvin fluctuations in those temperatures across the sky. So we need extraordinarily sensitive detectors. So in particular, this little animation here, this is the Planck Satellite scanning the sky. We just point the telescope at the sky and scan, and scan, and scan, and scan. And every 6 months, we cover the entire sky, and we carry on. We're currently on our 6th scan of the sky. You'll see a bar across the middle. That's the galaxy. The galaxy gets in the way. It emits the dust in particular, and synchrotron radiation emit quite strongly in the frequencies we're interested in. So we have this band across the middle. that's in the way. In an ideal world, we would go outside of the galaxy and make our observation. That's another one that's not going to get funded anytime soon. The nice thing about space is that you can see all of the sky, and you're above all the atmosphere, and you've got an extra degree of freedom in your scanning. It's great. The downside is it's extraordinarily expensive to go there. So as well as using these space observations, we also do suborbital experiments, either on stratospheric balloons. So this is the Boomerang balloon, about to be launched in Antarctica in front of Mount Erebus. The great thing about the Antarctic is that for about a month and a half, 2 months every austral summer, there's a circumpolar wind. So you sit on the edge of the ice at McMurdo Station, you send a balloon up, the wind blows it around Antarctica, and about 2 to 3 weeks later, it's back overhead. You drop it down, you go and get your data, and go home and analyze it. First flight worked beautifully. We landed 30 kilometers away from the launch site. Second flight, not so good. The wind stopped. The wind stopped while the balloon was floating over the Russian sector. The balloon, eventually, we just had to cut it, blow the explosive charge, let the balloon off, parachute the instrument down. The only thing within 500 miles of the landing site was a statue of Lenin. So they ended up having to do a fairly serious expedition to rescue the payload and get it back. But that produced a second data set. We have another balloon going to launch this winter, the EBEX experiment. Balloons are very nice because they get you above the atmosphere. The downside of them is that at the moment, the longest flight you can get is a couple of weeks. Now, there are some plans going on for ultra-long duration balloon flights, launching from Australia and going all the way around the Southern Ocean and giving you a 2 to 3 month flight. Unfortunately, the test flight didn't take off and landed on someone's car, and the ensuing health and safety violations and put the program back about 5 years. So the other alternative, if you want to get a very long observation, is to observe from the ground. Now, the trouble with observing from the ground is there's the atmosphere in the way. You know, we're doing a good job at getting rid of as much of that as we can, but it's still there. So the idea is to go somewhere as high as you can. So Antarctica is actually a very good place for being high and dry. It's extraordinarily dry in Antarctica. All the water vapor just freezes out of the air. Trouble is, you know, the best place to do this would be at the South Pole for the height and the dryness, and there are many telescopes at the South Pole. The downside of the South Pole is that if you're sat on the ground, one of your modes of operation to actually view some of the sky is to use the rotation of the Earth. So you point your telescope up in space and the Earth's rotating, so it scans across space. If you're sitting at the South Pole, the amount of space you view is limited. So there are telescopes at the South Pole. They do very good work, but there are issues with them. So another place to go is the Atacama Desert. Extraordinarily high, extraordinarily dry, up in Chile. And so this is the quiet experiment, sitting up in the Atacama Desert. I'm also working on another experiment called Polar Bear, which is sitting up in the Atacama Desert now. What are polar bears doing in the Atacama Desert? Well, originally it was planned to be an Antarctic experiment, but the funding changed and the name didn't. So we have polar bears in the Atacama Desert. So now we've gathered this data set, what do we do next? Well, here's what we get. An example. So we have a signal, in this case in nanovolts. So these are tiny, tiny, tiny signals. And it's just a long stream of noise. And in fact, you know, this noise completely dominates, even though we have cryogenically cooled detectors of extraordinary sensitivity. In fact, there have been, when the Planck Satellite was being put together, they wanted to check the mirror. And there was an offer from one of the intelligence agencies to check our mirror for us if we could flip the satellite and point it towards the Earth every now and then, but that one wasn't going to happen. So we get this time stream that's almost entirely noise, and the fundamental thing about these observations is that it's not white noise. So,
question, so that's for pointing the detector in one direction?
So this is the time sequence as a particular detector scans across the sky. So that's pointing at all kinds of, it's just sweeping across the sky. For the satellite experiments, it's sweeping around in a big circle. For balloon or ground-based experiments, you tend to chop side to side because you don't have that full degree of freedom. So you can chop side to side while the Earth is rotating, and that gives you a different kind of coverage pattern. But you're just scanning across the sky, gathering this timeline that is hugely predominantly noise, but somewhere hidden in there is the signal of the sky. And the way you discriminate between them is that the sky signal is the same every time you're looking at a particular place on the sky, but the noise is constantly changing in time. So you can use that. Now, obviously, if it was white noise, you'd just bin for you'd pixelize the sky, and for every pixel, you'd bin all the observations in that pixel, and that would drive the noise down, and you extract the signal. In this case, the noise is correlated. There are long timescale correlations in the noise, so you have to do something a little more clever, but not that clever. But when you do it, if you're lucky, you get a map like this. Well, you don't, obviously, because there's a galaxy across the middle. But if you do a simulation, you don't have to put the galaxy in. So here's a nice simulated data set. This is what the map of the sky would look like. This is the fluctuations. You can see that there are fluctuations on all different kinds of scales. There are sort of here's a large blob of cold sky, a large blob of hot sky, but even within that, there are hotter and colder blobs. So how do we characterize this? This is a particular realization of the microwave background. We'd like something that's more intrinsic to the data. Well, the angular power spectrum is the thing we go for. So this is take the spherical harmonic transform of the sky and average over all the M modes, because we have a belief and an assumption that the sky is azimuthally symmetric. So we're just looking at what's the power in the sky on different angular separations, on 180 degrees down to fractions of a degree. So the monopole is down here, and as we go up higher and higher in multipole, we're going to smaller and smaller angles. Sorry, I'll try and remember to do it over here. So this is the temperature power spectrum. This is the temperature cross E mode spectrum, the E polarization spectrum, and the B polarization spectrum, and these various features in it. So the location of this bump here tells you the geometry of the universe. The ratio of the heights of these bumps tells you the composition of the universe. These are basically, these fluctuations are imprinted by acoustic waves in the plasma. So you're basically seeing a series of harmonics. And down here in Nobel Prize 3 territory, we have the B mode. We have a B mode signal here that is generated by the gravitational lensing of the E mode signal. So the E mode polarization signal, as it travels through space, gets distorted by clusters of galaxies in the way they gravitationally lens it, and that converts E to B. But down here on the larger scales, we actually see the trace of the gravity waves from inflation. So whoever gets to detect this part, whoever is the PI of the experiment that gets this part, gets the Nobel Prize. So that's what we're chasing for. So we've got 3 generations. Planck is the 3rd generation satellite. So this was the COBE satellite that got this is the image generated by the COBE satellite that got the second Nobel Prize, rather, the first detection of the fluctuations. And you can see these are very, very smoothed out. This had about a 10-degree beam. So this really smoothed the sky on large scales. But as we've moved to different generations, the WMAP satellite and now the Planck satellite, we get to higher resolution and we start introducing polarization, a much fainter signal. Now, the higher the resolution you're going to, the harder it is to control the noise, the more noise there is. And if we're looking for polarization, the fainter the signal is. So this is where we get to the data challenge. We're trying to extract these fainter and fainter signals from the data. And the only way you can do that is to gather a larger data set. That gives us 2 issues. Firstly, we have to generate a larger and larger data set to get the signal to noise necessary. And secondly, we have to control the systematics ever more finely to extract these fainter signals. So you've got to get the systematics down to well below the level of the signal you're looking for. So you can see that from the COBE satellite, about 1 billion observations that got binned into about 10,000 pixels on the sky, just chop the sky up into pieces. This has evolved over time through Boomerang, the balloon experiment, so about the same number of observations, but on a small patch of the sky, so a much larger number of pixels, you could...
How do you quantify observations?
So the observations are the duration of the experiment multiplied by the number of detectors multiplied by the sampling rate of the detectors. So typically the detectors are sampling at between, say, 50 and a couple of hundred hertz. So that gives you the number of observations per second. Multiply that by the number of seconds in the mission and the number of detectors, and that gives you this observation number. And so there are various ways you can increase that's the number that we want to increase to get the higher signal to noise. We need to get more and more observations. So we can either observe for longer. Well, we're already observing for years at a time. So longer is challenging to get it up by the orders of magnitude we need. We could observe faster. That gets technologically tricky. I mean, we're already observing at hundreds of hertz. But you've got to pull all these samples off the detectors and read them into the readouts, so that's sort of that's a tough one to push too hard. Or you can get more detectors. So that's what we're going for now. So for instance, the Planck experiment has 74 detectors. The Boomerang experiment will have about 1,500. So there's a way by multiplexing we can now gather much, much larger data sets, the ones that we'll need. So as I say, we're going from billions to tens of billions, ultimately up to about, if we get a satellite beyond Planck, which is currently the sort of on the table, but is funding constrained very heavily, that's the kind of data set we'd look at gathering, 10 to the 15 observations. So if you follow this trail, you'll see that, not surprisingly, it follows Moore's law. A lot of the same kinds of technological advancements that drive Moore's law fold into astrophysical detectors. So all we have to do is to be able to handle a 1,000-fold increase in the data volume over the next 15 years. So all that means is that we need algorithms that will scale through the next 10 Morse foldings. Well, we've done it for the last 10 years, for the last 1,000-fold, but it is an ongoing process. And actually, this is one of the things that was the real revelation to me. And I came into the field, I'd worked in computational cosmology and other areas, saw this problem, this looks great, here are some experiments I can get involved with. I thought, we'll write the definitive, massively parallel CMB analysis package and the job will be done. Not quite that simple. It's a constantly evolving process. The data sets evolve, the challenges in them evolve, in particular the analyses, the control of the systematic effects, but also the supercomputers that we're using evolve. And as a result, we have to keep tweaking the analysis, the algorithms, and in particular the implementations to match the next generation of systems. So the analysis itself is, in principle, very simple. We just assume Gaussianity and maximize likelihoods. Gaussian likelihoods are nice and easy to write down. They're actually a very good representation of what's going on here, by and large. We can maximize the likelihood of the map, given the time-ordered data, and then the likelihood of the power spectrum, given the map. Unfortunately, in practice, it doesn't quite work like that. There are all kinds of systematic effects that get in the way, foreground sources. So we've got this whole galaxy across the middle, so you can cut that bit out, but now you've no longer got a full spherical surface, so the spherical harmonics are no longer a complete basis set. We've got breaks in the data. The detectors have beams associated with them. The beams are not perfectly circularly symmetric. So you've got asymmetric beams. That's going to convolve the sky with some complex function. The noise may not be perfectly non-Gaussian. So there are all these issues that we have to deal with. But in particular, the one that I'm focusing on here is this step-by-step evolution, both in the size of the data set and the architecture that it's being analyzed on. So here's the story so far. For the particular experiment, the Boomerang 98 data, that was the good flight. The B2K2 data, that was the flight that stalled over the Russian sector. The Planck single frequency maps. Planck has 9 different frequencies. We use the different frequency information to separate out the microwave background from the foregrounds. They behave differently at different frequencies, so you can use the different frequency information. The Planck using all frequencies, or the EBEX case, and then Planck Monte Carloing the data, or polar bear. So way back at the beginning, we had the nice, I loved the Cray T3E. It was a lovely machine. For the Boomerang 98 data, we could do explicit maximum likelihood calculations. The explicit calculations only scaled as the cube of the number of pixels. So back here, when the number of pixels was so we actually reduced the resolution. We oversampled, got this down to about 10 to the 5, and then we could do explicit maximum likelihood calculations on 100,000 by 100,000 matrices. Not a problem. Obviously, once you get up to 10 to the 9, 10 to the 10, a billion by billion dense matrix inversion is a little challenging. But here we could handle the full maximum likelihood solution doing explicit linear algebra operations. We had a big matrix inversion and a Cholesky decomposition and triangular solve. That all worked very nicely. That was the data from the balloon. That was the front cover of Nature data. By the time B2K2 came around, we moved from a T3E to an IBM SP3. Communication was much worse on the SP3. It was a much bigger system, but the latency and bandwidth were significantly poorer. So we had to change from doing a Cholesky and a triangular solve to an explicit inversion and multiplication. Less accurate, but less communication. So there's a trade-off there in speed versus accuracy. By the time we were dealing with the Planck single frequency data, we've gone up to 6,000 cores on the SP3. And we're now talking about the Planck data, so we're talking about hundreds of millions of pixels, can't do the dense linear algebra anymore. So we start having to use approximate methods. We can do a PCG of the maximum likelihood, a preconditioned conjugate gradient solution to the map-making equation. What we don't get out of that, then we get the map, but we don't get the noise covariance matrix that goes with that map. So we now have an insufficient statistic. And the only way you can then deal with that, when we want to get the power spectrum, is to use Monte Carlo methods. So instead of having an exact representation of the noise in the map, we now Monte Carlo that. Now, that's fine. You can Monte Carlo enough realizations to get the kind of accuracy you'd like. Unfortunately, the enough realizations, if you want 1% uncertainties, you're talking about 10,000 realizations. So we've now got to simulate and map 10,000 times the real data. So it solved the NP cubed problem, the number of pixels cubed problem, but it's replaced it by a 10,000 times the number of time samples problem. And as you saw, those numbers of time samples increasing by a factor of 1,000 over the next 15 years. So we not only have to do the analysis, but we have to do the analysis 10,000 times. So since we did this shift to these methods, it's basically been an evolution in the approaches to doing that. So going from 6,000 cores on the IBM SP, we now have we then had a Cray XT4 with 40,000 cores, big jump in the capability there, and we coupled the simulation and map making in a way that I'll describe. And finally, currently on the XE6, 150,000 cores, we're moving to hybridized codes, which I'll talk about as well.
So the last one being Hopper.
Yes. So this is Hopper. This was Franklin, Seaborg, and M. Curie. So here's what it looked like in practice, going from, as I said, we reduced it to about 10 to the 5 pixels, 128 T3E processors made us this very nice map of a patch of the sky observed by boomerang, and then pushing forward into a Planck temperature map, 10 to the 10 samples going into 10 to the 8 pixels. So we've jumped from 128 to 6,000 processes. You can imagine immediately that that's going to cause issues with I/O, with communication, up to the 15,000 cores to generate an EBEX map set, temperature and polarization, 10 times as many samples. And in this bottom corner here, this is 10,000 realizations, or this is actually 1,000 realizations in this particular image of the noise in the Planck detectors. So these are one of these Monte Carlo sets. So you can see all kinds of things if you stare at that and go cross-eyed a bit. But this is just the detector noise. But we have to Monte Carlo that eventually 10,000 times. There's only 1,000 here, and that was running on 32,000 cores. So what's our target? Well, we are legally required to publish Planck data in January 2013. So say ESA, the European Space Agency. So by the middle of this year, we need to be able to generate 10,000 realizations of the Planck mission, simulate and map. So that's, well, 3 of the detectors aren't working, so it's really 71 detectors, but that doesn't make a huge difference. And ideally, we'd like to do that an amount of time so that the people doing the data analysis aren't sitting around twiddling their thumbs for weeks and months at a time waiting for us to generate this simulation set. And we've only got a certain number of hours on the supercomputer. So our target has been 1 day turnaround, 1 million hours, 1 million CPU hours. So here's what we have to do to generate the data. First of all, we need to do a simulation. So our data is the sum of noise and signal, and the signal is a signal that's stationary on the sky. So it says, where are you pointing at a given time? So this is our pointing matrix P. At time t, I was looking at pixel P. So this is a sparse matrix vector multiplication here, and our noise. Generating the noise involves lots and lots and lots of pseudo-random numbers, and they better not be correlated. They better not be inadvertently correlated, because we're relying precisely on understanding the correlations in our noise. So if our random number generator introduces spurious correlations, we are toast. That's been a big issue. People have done some very ugly things with that. And then the signal stream scanned from a beam smooth sky.
Question, so how many bits do you use in your random number generator?
So we're using 64-bit.
Okay.
Actually finding a robust thread-safe 64-bit parallel random number generator has been challenging.
Okay.
So this is pseudo-random number generation and then FFTs. This is spherical harmonic transforms. And then here's the map-making equation, which is really just an AX equals B, but with various noise and pointing matrices included. But first of all, we build the right-hand side, so that involves an FFT to do the noise multiplication, and then a sparse matrix vector multiplication, and then we PCG gradient, again using the sparse matrix vector multiply for the pointing, and Fourier transforms for the noise multiplication because of the properties of the noise matrix.
Will you say more about which preconditioner?
I can. At the moment, we're simply using the diagonal. Okay. It's actually block diagonal because there's the temperature and the 2 polarization components for each pixel. Mm-hmm. So it's a 3 by 3 block for each pixel. Okay. We just take the block diagonal part of this matrix and use that. And that typically is good enough to get convergence within to 10, 20, 30 iterations. Okay. So in theory, this should all scale very nicely. It should scale linearly with the number of observations. If you get 10 times as many observations, it should take 10 times as long, or it should take as long on 10 times as many cores. Well, so what are the issues? Well, I/O. I mean, you know the hierarchy here. Data movement is what costs us. There are flops galore if we can only get the data to them fast enough. So that's pretty much the whole challenge at the moment is getting the data to the compute cycles fast enough to take advantage of them. So working up that hierarchy of things that get in the way, I/O is a huge one. I/O systems, as computers get bigger and bigger and bigger, the amount of money that it costs to scale the I/O up to the way that the funding gets assigned is primarily to the cores. Thank you, LinPack. Then to the communication, because you kind of need that to do LinPack. And the I/O gets sort of left behind somewhere. I've actually worked on systems that had essentially no I/O. It was a particular NASA system, which was kind of embarrassing given that they're all about collecting data. So for the I/O, we need to read. We need to know where the satellite was looking or where the instrument was looking at every time, and we need to know what data it gathered at every time. So we need to read in the pointing. If we're doing a simulation, we need to read in the pointing and then write out the time stream. Oop. If we're doing an analysis, we need to read in the pointing and the time stream and then write out the map. The data, the time-ordered data in particular, are distributed over all the processes. At every PCG step, we then need to gather the map from all the processes. Each process has part of the map. We need to gather that from all of them. So there's a gather operation at each iteration of the PCG. That dominates the communication. And the calculation, well, the upside is that we only need to use linear operations, so things don't scale too horribly. The downside is that we only get to use linear operations, so the amount of data reuse is very small. So the efficiency is challenging. Even once the data are on the process, there are inefficiencies.
So linear operations means the number of operations is proportional to the amount of data.
Right.
Yeah.
Yes.
Okay. Question, so is there a communication issue with getting the data out of the satellite in the first place?
No. That one gets funded properly because if you don't get the data from the satellites are somewhat harder because you have to send it back. With the balloons, you actually you send the data back in real time, but you also have it stored on the balloon and recover that at the end. Ground-based experiments are even easier. You just have graduate students shuttling back and forth between Berkeley and Chile, carrying duffel. Nothing like the bandwidth of a graduate student with a large bag.
Bad latency, though.
Sorry?
Can I be one of your guys? Call me a mule.
I've been trying to get that trip. They kind of laugh at experimentalists. I've been made to pose at times with a screwdriver standing next to an instrument, and they all think it's hilariously funny. So if you're good with screwdrivers and you can work at altitude, possibly.
How is the pointing being measured, and is the noise in the state estimation and the filtering on that correlation as much of an issue as?
No. So the pointing, we use a number of things. So in particular, we use star tracker. So you take a little image of the field that you're pointing at, and there's enough stars there that you can figure out exactly where you're looking. We use gyroscopes on board. There's all kinds of telemetry, and that's not affected by the noise to anything like the same degree because those are not nano-Kelvin signals. So fortunately, the pointing is typically very good. So here's what we used to do with the I/O, or when we the field started, here's what people did. So you'd say, okay, I'm going to do a Monte Carlo realization. So first of all, for every detector, I'll read in the pointing for that detector. I'll simulate the sky, and I'll write out the time stream for that detector. And when I've done that for every detector, I'll launch my map-making code. I'll read in the time stream and the pointing for every detector. I'll make a map out of it, and I'll write it back out. So that means that you had to read all of the pointing twice and write and read the time stream. So for the Planck dataset, that would have involved reading 500 petabytes of data, writing 70 petabytes. So there's a few years of compute time. Now, there's obviously enormous redundancy here. So how can we optimize that? Well, the pointing observations are not made at 200 hertz or even 30 hertz. They're much slower. You don't need to take those signals anything like as frequently because we're moving smoothly. So we typically sample at 1 hertz or 4 hertz and interpolate. So you don't need to read in the full dense pointing. You just read in the sparse pointing and interpolate on the fly. Moreover, you don't need to read in the pointing for every single detector. You can just read in the pointing for the bore site of the telescope, sort of where's the center of the telescope pointing, and then rotate that to any individual detector. It's kind of obvious stuff, but it's amazing how long it took to get people to adopt that. In fact, we're still one of the few groups that does that fully. There are a lot of people still spending an enormous amount of time first generating and writing out explicit detector time streams for every single detector. And then every time they want to do an analysis, reading those back in. Enormous redundancy. And then you're going to do the map making, you're going to do the simulation, and then write the simulated data out to disk, and then turn around and read it all back in to make the map. Well, let's combine the simulation and the map making. And finally, put the Monte Carlo loop inside the map maker so that any data that's common to every realization, like the pointing data, just gets read in once, and then you do the Monte Carlo, repeatedly using that same pointing data. So here's what we do now. Read in the pointing data, and then each detector on the fly calculates its own pointing, and then for each realization, simulate the time stream, map it, write it out. So now we're only reading in the sparse pointing, and we're only writing out the maps. So that gives us a 10 to the 8 compression in reading, and a 10 to the cubed compression in writing. That makes a big difference. The next challenge was the communication. So we see that as I say, we have this enormous amount of sample data, big time streams. We chop it up in time. In particular, given the way we're going to do the calculations, if we have a whole set of detectors, and here, this is time, it makes sense to put equal amounts of data on each process, but to stack the data like this. So this is process 0, this is process 1, this is process 2, and so on. Because all of these detectors, all of these samples share the same bore site pointing. The telescope was pointing in the same place for all of these samples. So we do a compression. So this process only has to read in this interval of pointing, whereas if you divided it long ways, then processors would have to read much more of the pointing. So having done that division, though, this process now carries all of this time-ordered data, and so it carries observations in all of the points on the sky seen by all of these samples. So that's some fraction of the sky. But not only does this process sees some fraction of the sky, but it doesn't see all of the observations in that fraction of the sky. So a particular pixel, a particular place on the sky could be observed by this process and this one and some number of them. So every process has some of the observations for some of the pixels. So at the end of every PCG loop, you've solved for your observations, you've then got to do this all gather. So the simplest way of implementing this, which we started with, just to get it, put a process and an MPI task on every core that you're using, distribute the time stream in this way, and then at the end of every iteration, use all reduce. Now that's kind of an ugly thing to do because every process for an experiment that views the whole sky, every process is only seeing a fraction of the pixels. So you'd zero pad out to a full vector, do an all reduce, and then just pull out the values you were interested in. So massive redundancy in the data volume, and most of the calculations you were doing were adding 0. But it worked. It was quick to implement. Not the best thing to run, though. So obviously the thing to do, a couple of things to do. Firstly, reduce the number of MPI tasks. As we go to the multi and many core systems, we can't run an MPI task on every process or on every core. Trying to do global communication across hundreds of thousands of cores, that way madness lies. So now we're only using MPI where it has to be used. So MPI for off-node communication, use threads on the core, hybridize the code. Similarly, you can want to minimize the total volume of the messages. So now instead of the all reduce at the calculation, every pair of processes figure out what's our personal overlap. Process 1 and process 0. Which pixels do we share? And then at every reduction, we just use scatter gather. So every process broadcasts a vector that's made up of these little pieces that say, this one goes to process 1, this one goes to process 2, this one goes to process 7, because I didn't have anything for 3, 4, 5, and 6, and so on. So a huge reduction in the data volume.
So when you say every pair decides if they overlap, that sounds like an n squared thing. Hopefully that doesn't happen that way.
No.
Okay.
Okay, so I think this is what I just, right. So there's actually a decision to be made. For all sky experiments like the Planck Satellite, where you're scanning on these rings, typically this interval will be something like 1 ring. So you scan around on a ring for half an hour to an hour, and then you move a little bit, and you scan on the next ring for an hour, and you move a little bit, and you scan on the next ring. And 6 months later, you've covered the whole sky. So these tend to be a single ring, so the overlap between pairs of processes is very small. In that case, the scatter-gather is much, much more efficient. For a ground-based experiment, or for a balloon-based experiment, you're staring at a patch of the sky and you're nodding back and forth. And then the sky is moving as you're nodding. And then periodically you get to the bottom of the region that the sky has moved enough that you've kind of got to the bottom of the region you want to scan, so you reset the elevation and start again. And those elevation resets tend to be the point where you break this data. So now every process is pretty much scanning the same section of sky. In that case, all reduce is the way to go. So here's the impact. This is on Franklin, dividing the simulation and map making into calculation time, communication time, and I/O in green. So you can see that as we got above about 4,000 processes, the communication just completely took over. This was trying to do all reduces of large vectors, most of.
So you'd like to pick to minimize the sum of those 3 costs.
Right,
okay.
Yes. And in order to minimize it, the first thing you obviously do is determine which one is dominating. And so at this point, having solved the I/O problem, it was the communication. So you can see that going from here to here, we've done 2 things. We've introduced threading. This was very early in the analysis, so the threading was pretty suboptimal. So you see the calculation time has increased fairly significantly. But the communication time has dropped by so much that we didn't even care at that point. So communication became negligible.
So just to make sure we interpret it, so the vertical axis is core seconds. So if that's pretty flat and you increase the number of cores, it's perfect linear scaling.
Right.
And so you use as many cores as possible. Okay.
Here we have Hopper comparing, again, the all-reduce with the hybrid all-to-all. And again, you can, now in this case, it's splitting it between the 3 steps of the operation, doing the mapping, the simulation, and the writing. But again, you can see, in particular, the mapping, which is where all the communication is. As you get to large numbers of cores, this just explodes. So the logarithmic scale, so this is bad news up here. So,
and again, it's the same scaling.
yes.
Okay.
So here's what we've been shooting for since we really started working in earnest on this in the early 2000s. This is what we were aiming for. So we need to be able to process a certain number of samples per second. That's the wall clock time to mean that the data analysts aren't sitting around waiting forever for us. And we need to do that a certain number of samples per core second, that's going to be the cost of running this thing in NERSC MPP hours. So we'd like to do 10 to the 4 maps on 10 to the 5 cores in 10 hours, orders of magnitude. This was the first code to run on all of Seaborg when Seaborg was increased from 3,000 to 6,000 processes. Unfortunately, at the time, when NERSC bought Seaborg from IBM, the MPI was hard-coded to have a 4096 MPI task limit. So when the machine was doubled in size to 6,000 cores, it was, oops. We'd really like to be able to use this entire machine, but there's this limit. So I think they did, SED in place 4096 to 8192. So that we should get a code to try this out. So we put this map-making code on the entire machine, and it took about 4 hours to do the map-making on 6,000 cores. The simulation had been done ahead of time, so this was just the map-making. This is now our standard debug job. It's about a 2-minute job on Hopper in the debug queue. So that's a single frequency of Planck, but this was with all of the data having to be read from disk and all that. This was the starting point coming in from the previous suborbital experiments. So this was the first simulation of the entire Planck focal plane, full focal plane 1. By that time, we'd introduced the data abstraction. I seem to have lost an image on here. So by that point, we'd generalized a lot of the data structures and improved the representation enormously. But then going from FFP1, introducing the on-the-fly simulation to avoid all the redundant I/O, that took us to here. And then introducing the hybridization and the communication bottleneck has taken us to this point. So we're now at a point where we can do these calculations. Oh. All right, that one's going there. So our current status, this summer, I will be running 10,000 realizations of the Planck mission on Hopper, delivering them to the collaboration. That's going to be a pretty substantial calculation, but we're down to, we can run that 100,000 way parallel on Hopper and generate about 1,000 realizations an hour. The interesting thing to note, though, for future work is the calculations obviously scale with the number of observations. The communication scales with the number of pixels, because it's all these map reductions. The I/O also scales with the number of observations, so we just try and minimize that away. Anything that doesn't need to be read in, calculation on the fly, always. But the communication is scaling with the number of pixels. So this kind of becomes an interesting point for the next generation of experiments. So between the Planck satellite and the CMB pole satellite at some point way in the future, we have we're going to have 2-3 generations of suborbital experiments. They only look at a patch of the sky. And in fact, the whole point of this is that we need to get more observations per pixel. So we're going to be changing the balance of calculation and communication in the right direction. We're going to do more observations per pixel is more calculation per communication. That's a good thing. So in the case of Planck, we've got about 1,000 observations per pixel. In the case of Polar Bear, we'll have about 1 million. The other interesting thing that this allows us to do, so an individual experiment has a certain data size. You're kind of stuck with strong scaling. But as you move between experiments, the data volume is increasing, so we can sort of use different experiments to exploit weak scaling. I'm going to skip this one because it's a very cluttered graph, but we've actually done a lot of work with this code, actually doing performance testing on HPC systems. So this was actually looking at 3 different crays on 200 to 16,000 cores, looking at whether it was just replacing the all-reduce with the all-to-all V, or it was just the hybridization, or both. And not surprisingly, the conclusion was you have to do both of those to really address the communication bottleneck. But this has actually been a nice kind of side angle to this project. In fact, some of these codes have been used in the NERSC procurement suites now. So unlike a LinPack, this actually requires you to do all of the work, do the I/O, and really stress the system. One of the nice things about working at the lab and being a friendly user of the NERSC systems is getting early access to new systems. It's kind of fun when there's like 10 people sharing a 150,000 processor machine, and you can write the script for a 100,000 way job and submit it, and it just launches. No queue time. I'll have one of those, please. But part of the job there is to try and break the system before they sign the check. So this code has been very effective. So with Franklin, it took me 40 minutes to take the entire system down. Hopper was fortunately much more stable, and this code was never able to crash it. Not that we didn't try, but there's just one other thing I wanted to quickly take a look at. So one of the things we've been facing in the last, particularly the current generation, the move from Franklin to Hopper, but even before that, going to Franklin, the jump from thousands to tens of thousands and hundreds of thousands of cores makes a huge difference to how you approach the problem. And we know that we can't just keep cranking up the clock speed, so multi-core, many-core, GPUs, all kinds of things that people are trying to do to keep Moore's law going without either ramping up the clock speed or using all of the power in the country to run the machines. So there's also some interesting issues that come up with that. So I wanted to quickly look at this case with Hopper. 6384 nodes with 24 cores per node. But it's not quite, well, it's 24 cores per node, but it's really actually more hierarchical than that. I guess Hopper's probably the machine you've been using. So as you know, it's 2 sockets per node, 2 NUMA nodes per socket, and 6 cores per NUMA node. So if you just trivially go ahead and say, right, I'm going to run this in the best way, the way that I know, one MPI task per node and threads on the node, then you're going to have cases where cores are going to be accessing remote memory, and you can start hitting NUMA effects. So what's the best way to run on such a system? So we tried it out. So this is, again, separating the simulation in blue, the map making in red, and the writing in green. The writing also involves gathering the map components from all the processes and one of them doing the write, because you don't want to have 150,000 cores trying to write simultaneously. And this is running in 3 different configurations, running one process with 24 threads. That would be the dotted lines. 2 processes with 12 threads. That would be the dashed lines. And 1 process with 24 threads. That would be the solid lines. So you can see at low concurrencies, in particular in this map-making stage, which is where you do all the iterative PCG.
Question on the vertical axis again. So is that the sum of all the core seconds or just the time to completion?
This is now the time to completion.
Okay, so picking the minimum of that curve is...
Yes.
Okay.
So here you can see that 4 by 6 is significantly faster. Again, logarithmic scale. 4 by 6 here is significantly faster than 2 by 12 or 1 by 24. And this is the NUMA effects. So these are doing exactly the same calculations, but in this case, it's having to access memory on the wrong NUMA node. But as we increase the concurrency, the communication cost associated with having, suppose we're comparing the 4 by 6 and the 1 by 24, the communication cost associated with having 4 times as many MPI tasks start to dominate. And once we get above about 10,000 cores, we switch around. And so if we want to work at very high concurrency, then taking the NUMA hit for the benefit in the communication is the way to go. So here we want to work 1 by 24, whereas here we want to work 4 by 6. Now, interestingly, if we look at the polar bear case, remember now we've got 3 orders of magnitude more observations per pixel. So the calculation to communication cost is complete, it's 1,000 times more calculations per communication. So now it makes sense to use the 4x6 in all cases. The NUMA dominates throughout. So one of the things that this tells us is that there is no answer. There is no right answer. There is no single right answer. And essentially, for every data set, for every concurrency, you need to do these experiments, and you probably need to do them in runtime, because every time you change the concurrency, the data distribution is slightly different. The good news is that we want to do 10,000 Monte Carlo realizations. And that means we can spend a fair amount of time in the initialization phase optimizing things, because we're going to benefit from that 10,000 times over. And it's 10,000 times the number of PCG iterations, so say 10 of those, there's 100,000 PCG iterations we're going to do. So even a small optimization, even a small improvement in the time to do one iteration is going to pay off 100,000-fold. So just to conclude, CMB is great. It's just, we're looking at the echo of the Big Bang. We're looking at I remember my home laptop was the first screen in the world that saw a picture of the Big Bang. That's every so often I have to stop and think about that. This is extraordinary stuff. We're getting to look at photons created in the Big Bang and use them to challenge our favorite theories of cosmology and ultra-high energy physics. But it is a bleeding edge computational challenge, and it continues to be because the data sets evolve as fast as Moore's law. So we have to be always sitting on state-of-the-art computing, and that means it's a dynamic problem. So my pipe dream when I started this, that we would just write the standard package and that would be the solution. Now, forget that. This is constantly changing. Every generation of data, every generation of machine, you've got to go back and look at things again. But the science we can get is absolutely dependent on this. So we face this as a fundamental challenge. People, the funding agencies are putting, in the case of Planck, about $1 billion to put Planck up and to take that data. So if we want to get the full science possible out of that $1 billion, which we better do, that's going to depend absolutely both on our computational capability in general, but most specifically on our ability to exploit that. Thank you.
Thank you. So are there any more questions?
So how high in orbit is the Planck satellite?
So the Planck satellite sits at the second Lagrange point. So here's the sun, here's the Earth, here's the first Lagrange point where the gravitational pulls are equal and opposite, and here's the second Lagrange point where the gravitational pulls are equal and in the same direction. It's an unstable equilibrium point. The advantage of sitting here is that as the Earth goes around the sun, the satellite is pulled around in the same orbit, and so we can keep the back of the satellite and all the shielding always facing the Earth and the sun. Because if any of this light hit our detectors, they'd be fried.
So is the communication in your PCG still a bottleneck, and would a clever algorithm be welcome there, or is it somewhere else at this point?
It's somewhere else at this point.
Okay.
We're always interested in cleverness. For Planck, it seems that we've kind of got it under control for Hopper. Mm-hmm. We're certainly interested, and we'll be putting in applications to work on Mira and Titan next year, and it'll be interesting to see how going to 700,000 cores pushes that challenge. Yes. But yes, at the moment we're calculation dominated, which is a nice place to be.
Yes, yes. Okay. And how many bits of precision do you need to get the right answer? That's another part of the design space that people are thinking about.
So far, 64-bit seems to be sufficient.
Could you get away with a lot less? Some people are thinking
no.
about, okay, you really need,
At least not without being cleverer than people have been so far. So we can certainly, if we run in 32-bit, we get different results than 64-bit.
okay,
Different cosmology.
okay. Okay, so let's thank the speaker again. I just want to make one more logistical announcement. So we're going to have a poster session, which I've posted. So we're also going to do the student surveys. So the Eta Kappa Nu folks will come around and pass out forms during the poster session, at which point I'll be stepping outside while you fill out the review forms somewhere at the end of your presentations here and before we go out in the hallway. Okay.